In this prototype, we are asked to write a prototype framework for the game of tic-tac-toe, allowing M agents to play on a board of some particular side, wherein the winning condition is where the first player achieves a certain margin of victory over the other players, scored by the heaviest weighted sum of winning sequences. Now, this is the case where somebody comes to you and says, tic-tac-toe, how hard could it be? It would take me a weekend. And then you look at the real requirements, and it's not, it'll take me a weekend. It is incredibly detailed and incredibly complex, and you're thinking, okay, we have a team of 75 people working on this tic-tac-toe problem. We might need to hire another 32 people, a couple of PhDs along the way, just to make sure we can solve it. Now, in the previous prototype, we weren't able to solve the weighted averages, the weighting of that. It's not something that we considered. We ran out of time for doing that. But here you can see where it's actually a pretty easy thing for us to add in, because if it's the case that we know exactly where the win occurred, then really it's just taking where the win occurred and then putting that into something like a pandas series and then index the line, multiplying that against what they're all weighted, and then doing some sort of aggregation, like a sum across all the wins. And so we have most of those pieces with very high confidence, over 95% confidence that they are possible, even though we didn't write any code for them. This is probably one of the most important skills and the most important pieces of judgment that you get from rapid prototyping and from live coding, where live coding isn't just a performative thing, it's part of rapid prototyping. Namely, being able to assess a tight bound of confidence over code that you actually haven't written. I never parse the input, but I tell you what, it will take me no more than 15 minutes, plus or minus 2 minutes, to parse that input. I'm pretty sure I can do it, and I'm not even going to do it until I'm actually asked to do that task, because I have such high confidence that it's possible to do. Assuming that the input looks the way it does, and the output is the way that I had hard-coded it previously. And if either of those assumptions change, of course, then my estimate may change, but I don't really need to write code in order to have a confident estimate given those particular fixed points. Now, in this particular case, we're looking to write some sort of framework. And one of the things that we find when we do this rapid prototyping is there are certain patterns that you can pick out and tie those patterns almost directly to Python structures. Anything that looks like an agent model probably is going to involve either on the heavyweight end object orientation or on the lightweight end some sort of coroutine. So I'm going to focus my time in this prototype writing the framework itself, plugging in really basic pieces, and thinking about how I'd write this as some sort of interacting coroutines. Here's why. I know that a coroutine is a very easy way for me to represent an extremely limited API of some kind of state machine, where in each state of that coroutine, I'm getting all the information I know about the world, and I'm yielding my response to that. So I know that the individual agent looks something like this. It's some loop that is going to run forever, because when it's asked to stop making decisions, you'll stop iterating through this, so that can be handled separately. And here, I guess the stopping condition may at most be that it's no longer able to make a decision, although oftentimes for these agent models, we don't even have to model that because something external tells them when to stop looking. And in each step, I'm going to retrieve some state, and I'm going to yield some decision. And this is my starting point for this code. Now, here, my simulation loop, or my gameplay loop here, is just taking each one of my agents, and it's just going to run through my agents and give them what the state of the game is. So this will have some stopping condition for the state of the game. This is where I manage the state of the game. So do something like this. If some condition, then we break out, and we'll leave this running forever for now. And what we would do is, clearly, this is an agent model. This is like a turn-based agent model, which is why we can just use a simple coroutine approach. Here, of course, bear in mind, I'm talking about coroutines as a generalization of generators. In other words, coroutines with lowercase c. If this were actually some sort of real-time simulator where the agents aren't locked to each person takes a turn, well, this actually may be then appropriate for coroutines with a capital C. And the idea more or less translates pretty much one-on-one to the different approaches that I will take. But here we're going to say that everybody works in turns. So what I'll have is, for each agent in my agents, you take turns, and the state gets updated given your decision, or depending on how much you want to trust this API, you may yield the new state. So you may have the ability to just alter the state object directly, and we'll have to assume that each agent doesn't cheat along the way. Or otherwise, if we are worried about them cheating, or we're worried about them having too much information and then having dependencies based on that information, we might just yield a decision. So if we start with the decision, then we'll do this. We will want to send into our agent what the state is, and then get out of it what its decision is. And then we'll want to compute our new state given some, decision based on that. And here I can even code some of these pieces. This is a state and a decision. And here this returns the new state, which in my case is just going to be the state itself. And here you can see I send something in and I get something out, and it's just going to run this forever. So let's actually run this. Let's say here's our simulation. Let's give it some agents, and let's just go through a couple of steps of this. And you can think here we probably generally either want to know the incremental state of the game, so the state as each player plays, like for visualization purposes, or we want to know the overall round level state. One thing is, because our number of agents is likely to be finite and small, it's probably the case where we can just get away from doing something like this. So we could yield a structure that is these are the plays that were made in that particular state. So here we do something like this. So here we're going to yield what the new state was and what the plays were, what the individual decisions that were made are. So I think that gives us what we want. And let's just kind of go through this thing piece by piece. And let's just see how this thing plays. Now, obviously, we need to define our agents. And here we're going to get our can't send a non-value to a just started generator problem. So, and let's see, this is right. One important thing about prototyping is you got to learn how to spell. You got to learn, okay, there we go. And here we have our agent. Oh, and this should be a list of these. So let's have two agents like that. And of course, we get a can't send a non-value to a just started generator. So this is where a couple of the flourishes, a couple of the little cute things that you can do in one line, they're actually kind of beneficial to do, like writing NYs in one line, just because it allows you to jam something together, move on with proving that this works, and then come and revisit. So here I'm going to use one of those little cute things, where we take a coroutine and we replace it with a thing that looks like a function instead. And, once you practice these things enough, they come to you just off the top of your head. And where they might not actually be as much of a gimmick as you might think. So here, and here I think we can always assume that this gets a value, so we could do this. So here this is a common pumping style transformation for the coroutine into something that looks like an object, which means we need a dummy yield here. So this would be the initial state that it gets, and this here is a dummy yield. So we actually don't do anything with it. So, and here, these agents now don't have to look like coroutines, they can just like functions, which is actually a benefit, because if it's the case that we want to actually move away from the coroutine to the more heavyweight object-oriented approach, then we can leave the simulation code intact, and this could just be something that looks like this, class agent with a call. So this is one of the reasons why I do like this coroutine approach, because it's so simple. This would be call with the state that returns the decision. And here I can either kind of linearize that state machine in the source text of the coroutine, or I can have this splayed out against multiple methods within this class. They're both formulations, and if this is a library that I'm using, I might even allow my users to create either one of these formulations and fit them into my simulation. But you can see there's often this kind of one-to-one correspondence between the approach that you take and how well this generalizes and how well it solves a problem. Now, here, clearly we're going through state to state, so now we know we need to have some representation of the state. Because we're working top down, what we might do is we might have some representation of the state as a simple data class, because we can fill in those details later. So we'll say the initial state is our data class. It's often the case whenever we're doing some kind of simulation that we want to know what each of the states are. And you can see since we're yielding each of these states, because we want to know in order to visualize, in order to identify how the strategy behaved over time, in order to debug it, it's probably the case that we probably want this to be immutable. And here you can see there are sometimes decisions that we make that are very hard to unmake. Taking a program that works with mutable data and then making all that data immutable tends to be something that is really tricky to undo or to do after the fact. And so one of the choices that we make when we're doing this rapid prototyping is try to identify where is it the case that a decision today is going to save me a lot of pain tomorrow because this particular phase change is just very painful. From immutable to mutable won't be very painful, but other way around, it's going to require a lot of churn in this code. And so this is one case where I might make my life a little bit harder, jumping a little bit ahead, because the possibility of saving me time down the line is quite high. And as I do more rapid prototyping, I'm going to spot some of these things over time. Complex APIs, it's very difficult to change those, which is why I like the coroutine. It's a very simple API, just a call with one argument. Mutable versus immutable data, moving from built-in types like tuples where you have to know the order of the fields and you have to unpack them to something like a named tuple or a data class. These are all cases where jumping ahead is with very high likelihood going to save me some time later. So here we go. We have that state. And I guess the same thing for the decision here. I don't actually think it's that valuable for us to mock up the decision as a data class from the perspective of, continuing to develop this code. But where I think this is valuable is I can show this to somebody and they can get an idea of what my code is able to do. They can see that I have a simulator that runs forever, and now I can, put some state here, like if not state.active, break. So now they can even see that I have some breaking condition, which can now be encoded here as a property. And here, let's do something like this. Let's just give it a random.choice, because we haven't done anything random yet. And anytime I work with random data, one of the things I always do is I always seed it, because otherwise the output bounces around way too much, and it just becomes really, really tricky. So here, and you can see that random.choice hit pretty quickly, so maybe we need to weight this. The random modules choices where you weight them is a little bit ugly, so I'm just going to do this in a super hacky way. So we're going to make this 10 times more likelihood to be true than it is to be false, like that. So here you can see it ran for at least 3 steps. And what I can do is I can actually write out a little bit more of what the script level analytical code would look like. It would be like for each state and the plays in my simulation. And I don't think I need to package those up. I think this is a case where it's unlikely that I'm going to get more than the state and the plays. Anything else is just going to carry along with one of those 2 objects. So I'm pretty sure that I can stick with just a tuple there. And you can see here this runs for some amount of time, and I can go to my user and say, look, here you can see my framework. This is what you have to plug in. You can see that in your analytical code, you can iterate through all the states and all the decisions that were made. You can see that you can play this with multiple agents. And the rest of this is really just plugging in the pieces, namely, going into the state object and plugging in what it means for this thing to be active, what it means to transition. Here, I might do something like with decision that takes the decision and return some sort of copy. And the data class makes this quite easy. There's the dot replace. So I might do something like, with replacing self and then some particular field. That can also mean that if I'm passing mostly symbolic objects around, then I might be making a lot of copies of this data, but I'm not making a lot of copies of the expensive data. It might actually be, only storing the unique entities because everything else is just a reference to the underlying object that I'm referring to here. So if I do that, then the last piece that I might do is I might say the transition here is not this compute, but it's this state, with decision. And I'm actually quite happy with how this lined up because I have very high confidence that if this gives the person the data that they need in order to be able to build whatever they need to build on top of this, like a strategy comparison simulator for the game of n-dimensional tic-tac-toe, they can do this. Every other part of this I've already solved with the underlying problem itself. And even things like, how do I decide when to start this or stop this? Bear in mind that because I've modeled this as a generator, I also have the ability to stop the iteration externally. So here I could encode any arbitrary predicate using this information to stop this simulation. So I'm fairly confident that even though this represents a minority of the actual functionality, this represents a majority of the difficulty, and I've proven that it's possible to solve this. This is the value of live coding. This is the value of prototyping, proving that something's possible so you can get a tight bound on the variance of how much time and how much effort is it going to take to solve this problem.